The layout has since changed since our last seminar.
The layout.
It starts say instead of saying we're broadcasting, it says the content is being sent to the third party.
Oh,
The Zoom setting, I think. Yeah.
yeah. They keep updating the app.
Yeah.
So,
Good.
but
Looks like
yeah,
we're
it looks
live.
like yeah, it's working.
All right, cool. I think people are still coming in, but maybe since it's already 1, shall we start our seminar now?
Yeah, let me start recording, and then
Yes, please.
you can go ahead and start. One sec.
All right. Hello, everyone. Welcome to the 121st online Spintronics seminar. It's been a few months since our last one, and I hope you are all doing well, and thank you for your continuous support. It is my great pleasure to introduce today's speaker. Dr. Kelly Luo is a Gabilan Assistant Professor of Physics and Astronomy at the University of Southern California. She started in 2023. She was previously a Presidential Postdoc Fellow and Honorary Kavli Fellow at Cornell University studying spin-torque dynamics in van der Waals magnets with Dan Rolfe, King-Fan Mak, and Jay Shan. She received her PhD in physics at the Ohio State University studying information transduction between spintronic, photonic, and magnetic states in two-dimensional hybrid systems under the guidance of Roland Kawakami in 2019. And before that, she obtained her Bachelor's of Science in Physics at the Hong Kong University of Science and Technology. So without further ado, Professor Luo, you have the floor.
Sure. Thank you, Sing, for the nice introduction, and thank you for the organizer to invite me to give this talk. Yeah, so today I want to take this opportunity to talk about our recent work in spin orbit working magnetic heterostructure with a focus on van der Waals system, especially looking at the exchange interaction and how we develop ultrasensitive Sagnac magneto-optical interferometer to detect spin torque dynamics. So my name is Kelly. I'm the group leader of our newly established ultra-fast quantum optical spintronics group at University of Southern California. Yeah, here's our group website. So I wanted to start my talk with a brief introduction to this field of 2D magnets or 2D material, which is really a new material playground that was newly emerged in the past 10, 15 years. So this was, as a lot of you know, this pioneered by Andrew Gein and Konstantin Novoselov for the 2010 Nobel Prize in Physics for the groundbreaking experiment regarding the two-dimensional material graphene. And graphene had this very nice atomic sharp interface where the atoms are still strongly bounded in the XY direction, but loosely bounded in the Z direction. So this allowed us to create the designer type of structure layer by layer precision because the Z direction is coupled by this weak van der Waals interaction. And because of that, we can in lab using a Scotch tape to isolate the a single layer of the graphene. Let me try to get my laser pointer. And then we're able to use and then reconstruct model 2D materials layer by layer, and this allows us to achieve high tunability through electrostatic gating and surface absorption, proximity effect, etc. Yeah. So since the discovery of the graphene, which is in 2004, there's really a big zoo of like 2D van der Waals materials, and for realizing almost all domains of condensed matter physics to this day. So graphene was discovered in 2004, and shortly in 2010, the first optically activated 2D material, transition metal dichlorogenide, was discovered. This was first demonstrating a very bright photoluminescent signal in the molar layer MOS2. And for a few years, people have been looking for like the true 2D spintronics material, which is about a 2D magnet. So what about spin? In 2017, the first 2D magnet was discovered. This was realized in chromium triiodide, where people are using optical readout to show that there's a very nice out-of-plane hysteresis, out-of-plane magnetization down to the monolayer. So since then, there's really a wide range of different kind of 2D magnets. I'm just highlighting a few that are of high interest to the community. For example, chromium iodide, which is the first discovered 2D magnet that has DC magnetic coupling and also have interlayer antiferromagnetism, and chrome sulfur bromide, which I'll spend a lot of the time today talk about, which have triaxial anisotropy and also have interlayer antiferromagnetic couple, but intralayer ferromagnetic couple. And another two materials are of the interest of community, such as iron phosphorus sulfide and nickel phosphorus sulfide, all have different kind of spin ordering, either it's E-syn or XXC, and also have very intricate intralayer antiferromagnetic coupling. Yeah, so our research is really accelerated by this wide field of 2D magnet, and we're looking at different aspects of 2D magnetic structures to explore new interference phenomena and technology. So I wouldn't go into try to cover all the topic today, but this is sort of like a broad view about different kind of concept of devices and physics that one can achieve by using random orbital structures. I will try to focus my talk on more on the magnetic tunneling junction and also spin orbit torque. And also I have done some past work in auto spintronics and then charge to spin conversion, and these are really different kind of frontiers of Van magnets. Yeah. So our lab right now is at USC. It's an ultra-fast quantum optical spintronics lab. We are a new lab. We started in 2023. So this is sort of an overview of the capability of our lab. We have two helium-free optical microscopy crowds that with superconducting vector magnets. Both of them allow us to conduct most of our optical measurement down to 1.8 Kelvin and up to 9 Tesla. And we're also in the process of setting up an ultra-fast laser and also having operational fiber-based Sagnac interferometer that I will talk about later today to let us achieve high optical sensitivity amount of those magnetic structures. And we're also equipped with state-of-the-art glove box and of course also outside transfer tool with there's allow us to achieve exfoliation and construction of the devices in a airframe environment, and also have capability to interface with UHV suitcase. And yeah, and we are also equipped with our nano fabrication facility on campus where our students work on them most of the time. And this allows them to integrate together to really allow us to pursue this different kind of magnetic structures at the down to the atomic thin layer, and then also using advanced optical techniques. Yeah. So with this, I wanted to give a little bit of background or motivation about why or how we use manipulating magnetic material using electron spins. So in industry, one of the concepts that's now really as a mature technology in industry is this concept called spin transfer torque. Essentially, this is embedded in the existing MRAM technology, where most of the major silicon foundry has offered as a standard option in about 5 years ago. The concept goes like this. So the structure goes with a tri-layer structure where you have a ferromagnetic free layer and a ferromagnetic fixed layer sandwiched by a non-magnetic tunneling barrier. So this is basically a basic concept of one writing bit, magnetic bit. And then the electron is flowed vertically through the structure. So when the electron exiting from the fixed layer, the electron will become polarized by the fixed layer. And if the polarization of the electron is antiparallel to the magnetization of the free layer, this electron will transfer its angular momentum to the free layer and therefore exerting a torque. So this process of exerting the torque and being able to switch the free layer such as align with the electromagnetic direction is basically the concept of spin transfer torque. But for us, we look at this structure and we realize there is a fundamental energy efficiency limit in the structure. In that every electron can be polarized once and going through the vertical structure and then depositing the angular momentums and then leaving the structure. So there's a fundamental maximum frequency of about 1 unit per h⁻²per unit charging current. Okay. So in the lab, we're developing a new concept called spin orbit torque. This was, instead of using a tri-layer, now we're using a bi-layer. We only use one layer magnet and then integrate it with a layer that we call the spin source layer. The spin source layer is typically a layer of a large spin orbit coupling. It could come from spin moment locking state in coupled surface state. It also could come from bulk spin Hall effects, such as platinum and cobalt and platinum and palladium and such. But so in this layer, when you pass the electron laterally and in the spin source layer, the electron is able to get polarized many, many times and depositing its angular momentum onto the magnet before exiting the spin source layer. So that helps fundamentally overcome this efficiency, energy efficiency that's intrinsic in the spin transfer core. And to this day has been demonstrated by topological materials such as bismuth acetylene has the largest spin to charge conversion rate in the spin orbit torque concept. So for this, I wanted to sort of give an outline to the talk I would like to introduce today. So we will talk about, first I'd like to talk about how we achieve electrical detection of antiferromagnetic resonance with electrical tunable damping from the spin orbit torque from a topological material. And then I would want to spend some time talk about a recent work on manipulating the exchange bias between the van der Waals antiferromagnetic and ferromagnetic crossover bromide and iron germanium telluride, and using that to achieve a field-free spin orbit torque switching. And last, I wanted to introduce our recent development, this high sensitivity magneto-optical DC readout based on Sagnac optical interferometer. So this first, I will start with the first part, and here are the two papers I will be mainly talking about. So for the first part of the work, we focus on this new material crossover bromide, which is an A-type van der Waals antiferromagnet. So this material has a unique triaxial magnetic anisotropy with a magnetic easy axis within the van der Waals plane with optical identification. So if we look top down on the A and B axis, the spin within each layer are aligned along the B axis. And if you look side view, then each layer, the spin are antiparallel to each other. So interlayer, they are antiferromagnetic coupled, and intralayer, they're ferromagnetic coupled. And this is a picture of a crystal that we measured, and the crystal grows in a non-needle shape. This is grown by Xavier Roy's group in Columbia University. This crystal allowed us to identify the easy axis, which B axis is the short axis that of the individual single crystals. Okay. So because of the interlayer coupling is van der Waals coupling, this is a weak coupling. The antiferromagnetic resonance is in the gigahertz range, and this material is also very interesting from the optical perspective. The people have shown that it has strong and tunable X-con-magnum coupling, so straining and through gating, which will not be my focus my talk, but I give some of the references here. So first part, we looked at this material, and the first thing we wanted to really understand and study is how we can identify those magnetic anisotropies and how we can use them to control the magnetic resonance of the material. So we know that the hard axis is along outer plane C axis, the intermediate axis along A, and the easy axis along B. So then we proceed with putting this crystal on a co-planar waveguide, and then we apply magnetic field along different directions. If we apply the magnetic field perpendicular to the inclined easy axis, we will have this kind of spin flop configuration as moderate field, and with high field, we'll have both spin aligned, both sublattices aligned and become like ferromagnetic-like state. And if we apply magnetic field parallel to the inclined easy axis, at low field, we will still fighting against the exchange of the system, but at some point we'll have a strong, a sharp spin flip transition because of the two sublattices rotate in line with the applied external field. And with increasing external field, we will have a spin flip configuration that eventually will also have a parallel configuration. Okay. So this is what we think that what the material should be here. So we go forward and we start conducting experiment. So the first configuration we measure is the field perpendicular to the inclined easy axis. And by doing such, so this is a measurement that we took, we were able to measuring the microwave absorption along the co-planar waveguide and looking at the apply external magnetic field and looking at microwave absorption. And we do see that we can detect two modes. The blue is the theta, and then the dashed lines are the theta mode. We see in-phase mode, and we saw which is slightly lowering the energy at low field, and we also see an out-of-phase. And we proceed with essentially model these two modes. The in-phase mode that we found out is the acoustic mode, which they are in phase with each other, and the out-of-phase mode is the optical mode, which is slightly higher energy, which is out of phase with each other. And we're able to fit it to these two modes using a two sublattice LOGS mode. And then we apply the magnetic field parallel to the inclined easy axis, and then now this is a spectrum we obtain, and then on top of that we can try to analyze the spectrum. Again, in the low energy, in the low field region, we have this right-hand mode and then the left-hand mode as a direct consequence of solving the LLGS equation based on LLG equation based on two spin sublattices. And with an intermediate field in this figure around 0.24, we see a sudden jump in the spectrum. This correlated to the spin flip transition. And we see another mode over here that resemble a spin flip candidate transition, a spin flip mode that's a candidate of the two spins. And then a high field where both spins align, then we can also fit it to the high field mode when they're mostly like the two spins align with each other, similar to the ferromagnetic modes. Yeah, so by doing this, now we have established that by applying magnetic field along different crystal axes, we can really achieve different kind of antiferromagnetic resonance mode. So next, we want to look into how we can control the mode couplings by the direction of the magnetic field. So here we proceed with applying magnetic field within the inclined direction, but sweeping along the inclined axis. And then we can see that as it's sweeping along the b-axis by equal to 0, and as the increasing and changing the angle eventually along the a-axis, we can see this evolution of the left and right-hand mode into this optical and acoustic mode. And we can also see that at this at the intermediate angle, we see this mode-to-mode coupling, and we can really quantify this mode-to-mode coupling in the way that we are able to show that this two-fold symmetry brokenness within an inclined magnetic field, and we can achieve the strong magneto-magnet coupling between the outer phase and the in-phase mode by applying the magnetization, by applying a magnetic field as an angle in between the two axes. Yeah. And we can also further quantify this opening of the two modes, the coupling of the two magneto modes, and show that this is in the region of strong magneto coupling because the opening is much wider than the non-universal. So here we have shown that we can really control the magneto modes in the bulk and by different magnetic field, and also tuning to realize this different magneto modes in the bulk region. So the next thing that we ask ourselves is how do we achieve these different kind of magneto modes at low dimension, say down to field layers, and how do we achieve that? Can we integrate that effectively into a spin physics? So we take inspirations from recent work on the magneto-exciton coupling, where a couple of recent work has shown that a very interesting recent work showed that one can detect the resonance dynamics of the van der Waals interferometer using optical method, using its exciton optical coupling. And then we ask ourselves is how do we integrate the optic part, and then how do we achieve this kind of measurement down to a few layer, not down to 2 layers, onto a device region. So we take inspiration from the early work that constructed on chrome iodide, where people have shown that by sandwiching a few layer chrome iodide in between two graphite contacts, one can construct an MTJ device, magneto-tunneling junction device, and using the tunneling current to read out the magnetization state. Here, just taking some of the data from the previous work that's showing that when you are varying the magnetic field autoplane, when you're changing the spin configuration of the 2 layers, you can have a tunneling readout, magneto current tunneling readout, where the different zero bias conductance will show different states of the magnet of the spin alignment. So we went ahead and construct a similar sample. Here we're using a 3-terminal. I will explain why we use 3-terminal later. But here we essentially constructing closed circuit magnetism down to 2 layer, and on top of a platinum telluride, which is a direct signal metal for spin torque excitation, which I'll explain a bit later. But we basically measuring between tunneling readout from the T3 to T1, basically tunneling through the graphite contacts, from the graphite contacts through the 2-layer closed circuit into the platinum telluride. And this is a picture of our device. And we can also realize that we see that we have reproduced that what people has demonstrated on chrome iodide, where we measure the tunneling resistance, and then we can apply the magnetic field either parallel or perpendicular to the z-axis, and we can show the different kind of transition, either a spin flip, which is a sudden transition here, or a gradual transition, depending on whether the magnetic fields are applied along the EZ or the intermediate axis. Okay. So now we have shown that we can achieve the same kind of tunneling resistance readout and in the DC region for the different spin configuration. Then we move on to thinking about how we're using electrical detection of antiferromagnetic resonance. So here we use this again. On the same straight terminal sample, we pass our microwave excitation in the T1 to T2 region, and this excites a RF current that is passing through the cones of our bone. And our detection is from the straight third terminal is from the T3 and then T2, and then now we can using this reference signal here that we can also measuring out the magneto resistance that related to the time resistance of the readout. So in a nutshell, we're basically passing a RF current signal as an excitation of the magnetic resonance, and we're using the magneto resistance response in RF region to read out the overall magnetic resonance. And because if you have two RF signal, omega and another omega, this will become a cosine 2 omega. So this will become a DC signal as a rectifying signal. So we can have a rectifying signal from an RF source and using a DC voltage to read out the magnetic resonance of the system. So we went ahead and performed the measurement. This is a picture of our device where we have these are the three T1, T2, T3. We have in this particular device, we have a WT2 as a spin source, and we have a consumer on the top, and then we have a graphene contact on the tunneling contact on the top. So again, we verify that with DC magneto resistance by finding the magnetic field, we can directly read out the spin configuration through the magneto resistance readout. And then we look at the RF straight terminal mixing voltage, and we do see that at a certain magnetic field and a certain frequency where we match up the antiferromagnetic resonance, we see this increase in the mixing signal that indicating that we have a DC mixing signal readout of the antiferromagnetic resonance. So comparing left and right here is I'm showing that the our readout on the straight terminal bilayer consumer line, looking at the mixing voltage, and we have qualitatively a similar behavior than what we're measuring onto the bulk signal, bulk crystal using the microwave waveguide absorption. So here we demonstrate that we can achieve the antiferromagnetic resonance detection down to the atomically thin layer, and we can show that they have quantitative agreement with the bulk movement. So then, based on this advancement, then we proceed to try to control the magnetic resonance here using our spin source, using a spin orbit torque coming from the direct material underneath. So before I go into the detail, I wanted to give a little bit background of how one can detect the effect of spin orbit torque on the magnetic damping. So the simplest model to start with is to think about how spin orbit torque affects the ferromagnetic damping. The damping of the ferromagnetic resonance can be derived as a correlation to the intrinsic damping plus a term that is scaling with the current that comes from that generates spin orbit torque, and also cosine theta. Theta is the angle between the spin direction injected into the magnet and the magnetization of the magnet. So as in measurement, what people have shown that depending on whether the magnetization is positive or negative, or either aligned or anti-aligned with the spin direction, this cosine theta will have different sign. And this has been realized in previously shown that in the 3D magnetic system, where one can measure the mixing voltage as one varying the applied current, which is varying the damping IDC, and also varying the direction of the magnetic field. As we're varying the direction of the magnetic field, you will see either a positive or negative dependence of the line width. And as you're increasing or decreasing the current, you will see a linear dependence on the current. So this is the picture of a ferromagnetic resonance. Okay. So here we're looking at something different than a ferromagnet. We are looking at two sublattices, which is the antiferromagnetic resonance. So I just explained that in the ferromagnetic resonance, we only care about one spin lattices, that whether it's aligned or antiparallel with the injection spin direction. But in the antiferromagnetic picture, depending on how we apply the magnetic field, we can either align one of the spin lattices called the red spin lattice, or the blue spin lattice, depending on whether the magnetic field is positive or negative, which means that we can selectively align one spin lattice versus the other spin lattice. So this is what our system allows us to do. So we went ahead and then construct this sample where the constant bromide is 45-degree aligned with the current channel. And we can also apply different magnetic field along either the easy axis or the spin fold axis or the intermediate axis, and then again show that we can read out the magnetic resistance that corresponding to a different spin configuration. And then we proceed to measure the RF excitation, the DC bias induced line noise modulation. Here we apply external magnetic field, either positive or negative, to the that's either aligned or antiparallel aligned with spin direction. And we found something interesting that is not observed in the ferromagnetic system, in the sense that the negative magnetic field, we see a non-zero line noise change with varying DC bias. But as a positive magnetic field, we see a zero line noise change with varying DC bias. So to compare these data side by side, in the negative field region, where we are basically aligning, say, spin lattice 1 along with the spin direction, and in the positive magnetic field, we're aligning spin lattice 2 along the spin axis. And the fact that one of them we see a non-zero line noise change with varying DC bias, and the other one see a zero line noise change, this shows that the spin orbit torque is actually selectively excite one of spin lattice versus the other. In this case, the selectively excite actually spin lattice 1 versus the it's not exciting spin lattice 2. So we can extracting out these spin torque modulation depths by perform this line noise modulation measurement with varying applied current. We can also show that this phenomenon holds for all the applied current that we're able to measure, and confirm that the spin orbit torque modulate the damping of the AFM lattices, but they also only selectively excite one sublattices versus the other. And in the detail of our work, we also have fit onto the slope and then let us extract our spin orbit strength is about 0.29. And this is from platinum ferrite. It's about 3 times larger than platinum. So it's a reasonably good efficiency here. Okay, so with this, I want to move on to the third topic the second topic I want to talk about today, which is the exchange bias between the van der Waals antiferromagnetic and ferromagnets. So the motivation of this work is we wanted to really utilize the interfacial phenomena in van der Waals magnetic structures, where really like 2D structure is ideal for structure interface to study interface effects such as exchange bias, because they are so compatible with without the needing of sub-lattice matching, and they also have atomic sharp interface free of defects interdiffusion. So in this work, we really wanted to control and construct the different kind of magnets and taking advantage of the exchange interaction and the van der Waals interface, because of this is due to the fact that the van der Waals interaction is a weak interaction, so that the interface effect will be can be comparable to the interlayer interaction within each material. So this gives us the possibility to produce a spatially non-uniform spin configuration that's not readily achievable in a conventional magnet. Because in a conventional magnet, the within the material itself, the exchange is much stronger usually than the exchange at the interface. Versus here, a 2D material, because within the material itself, the bulk exchange is weak, the interface has a chance to play a more dominant role in the overall behavior of the magnetic system. Okay. So, yeah. And then because of that, there are phenomena beyond microspin response and remain to be unexplored. So the measurement we did is to construct this van der Waals structure using a few layer of constant bromide and a few layer of iron germanium telluride. The material growth is constant bromide from Columbia University and iron germanium telluride from Oak Ridge National Lab. And then we can see that we are able to really construct this quite nice atomically clean interface microscopically. Of course, macroscopically, there will always be bubbles, that we haven't figured out how to avoid that yet. But we can construct this structure, and then we can place this on a platinum electrode, which platinum serve as the spin source. We do this by a standard mechanical dry transfer onto a pre-platinum platinum electrode inside the glove box. And because iron germanium telluride is a metallic ferromagnet versus constant bromide is a semiconductor, this will give us, by doing this platinum hole bar, this will give us, due to the parallel conduction, a electrical readout of the autoplane magnetization through the hole resistance. Okay. So that's what the first measurement we did. we go ahead and measuring the Hall resistance of the system. And the y-axis is the Hall readout, the Hall resistance, the x-axis is the magnetization, and we do this for different temperatures. The very striking feature here is that there's a strong temperature dependence in the Hall signature. And the characteristic temperature that we care about is the neo temperature of constant light, which is 132 Kelvin, and the TC, the pure temperature of antimatter telluride, is somewhere between 160 to 190 K. So we can see that at 140 K, we have, which is this red curve here, we see a square outer plane hysteresis, which is characteristic of antimatter telluride with perpendicular magnetic anisotropy and uniform outer magnetization. However, at 30 Kelvin, we see this loop is far from square and showing a strong reduction in outer plane magnetization and zero magnetic field. So this gives us a direct observation of an in-plane exchange bias that comes from the constant bromide acting on iron germanium telluride, which produces a very large tilting angle of the iron germanium magnetization away from the outer plane field direction. And we can quantify how big this tilting is with different temperature. And we can see that average tilt as large as a 50 degree and low temperature for iron germanium thickness about 10 nanometer. So this showcases that at the thickness region of around 10 nanometer, the interface exchange coupling comes from constant bromide is really very strong. It's allow the iron germanium layer to have a tilting about 10 nanometer. Just a reminder that because iron germanium telluride is much more electrically conducting than constant bromide, so our Hall readout is basically reading out the magnetization of iron germanium telluride and not sensitive to the magnetization of the constant bromide. Okay. So, building on this observation that we have a strong exchange bias, we went ahead and constructing and then exploring the spin torque switching behavior. So here I'm showing two devices that the constant bromide is aligned differently on the platinum current channel. For one, the EZ axis or spin axis are aligned perpendicular to current, the other one is parallel to the current. And then we went ahead and then we did this current-induced switching measurement, where we essentially passed different kind of pulse current. This is a quasi-static measurement, pulse current. And then we measure the Hall voltage. Using the Hall voltage, the readout of the magnetization of the iron germanium telluride. And we can show that at zero apply external magnetic field. One of the configuration we don't see an obvious spin torque switching. This is the signals within the noise range, and within the other configuration we see a quite obvious deterministic spin orbit torque switching. And this direction where the neo axis is parallel to the current is also matching with our understanding that the exchange bias has to be perpendicular to the spin injection into the system, such as which provide a symmetry breaking field that allow for a deterministic spin orbit torque switching. When we can also compute this measurement in a more systematic manner, where we also apply different external magnetic field along positive or negative direction, and then we can show that for the direction that the exchange bias is not along the symmetry breaking field, we can still create a deterministic switching by apply external magnetic field. And versus for the other direction, where we observe deterministic switching and zero magnetic field, we can also apply external magnetic field to quench the exchange bias, which is essentially the external magnetic field is canceling the exchange bias, such that we will have the non-spin torque switching, and in the other direction where the exchange bias work together with external magnetic field, we'll have even a stronger spin orbit torque switching, larger spin switching behavior. Yeah, so from this, we can also measure the below and above the neo temperature of the crossover moment, where the source of exchange bias come from. And again, we're measuring along the direction that we can see the deterministic switching. And when the temperature is above neo temperature, which is 140 Kelvin, so the temperature is 117 Kelvin, we no longer see the deterministic switching anymore. Then we can overall see a much weaker spin torque switching with applied magnetic field. This is also consistent with the picture that the exchange bias coming from the magnetization coupling of both crossover bromide and iron germanium telluride, so that the temperature has to be below the neo temperature, below the magnetic transition temperature of both material in order to have this, in order to observe this exchange bias behaviors. And lastly, we finished. We sort of did a systematic measurement of the temporary dependence of this exchange bias. We measured the exchange bias by basically measuring the field, the applied field that will clinch the spin torque switching, and we can further confirm that when along the axis where the neo axis parallel to current, which is required for the symmetry of spin reversal switching, we can see a gradual increase of exchange bias down to about 5 Kelvin, and along the other axis that it's not symmetrically allowed down to 5 Kelvin, we don't see any exchange bias behavior in the spin torque switching. And the extracted value of the exchange bias also quantitatively agree with our bulk and anisotropy measurement and the exchange parameter of the cross-ripple band that we measured earlier. So with this, I would like to move on to the third topic, which is our high sensitivity magneto-optical DC readout, our recent development using Sagnac optical interferometer. So one of the reasons we are motivated to develop this high sensitivity readout is because a lot of those 2D magnets, because they have a very small amount of net magnetization, it's challenging to detect using conventional methods. So with that thought in mind, we started to develop different kind of ways we can have really achieve high sensitivity magneto-optical readout. So the method we adopt here is called Sagnac interferometer. This was based on Stanford group and opportunities group that developed in the I think in the 80s and 90s to detect symmetry breaking in unconventional superconductor. And this is just a showcase of our system where it's a fiber-based system. It's a combination of fiber-based and free space system, and most of them are pretty compact. This is a room temperature system that we developed at Cornell, where a combination of free space optics and a 15-meter PM fiber loop, which sits in a white box over here, and this fiber coupled to the top of the objective and essentially on a sample, which sits on a projected field electromagnets. And here on the left hand, I showcase some of the outer plane hysteresis we are paying on Sagnac, and this is a measurement of this takes about 10 minutes, and it's as a comparison to the conventional polar mode signal, we have at least a 50 to 100 times better signal to noise. This is on the platinum cobalt device, and we can further quantify the noise is around 5 microradians per square root hertz. We're not at the short noise region yet, so we still have a lot of space to further reduce the noise. So the next thing I want to talk quickly about how the Sagnac, how the setup works. So I talked about our Sagnac starting with a free space optics with a 770 nanometers super luminescence LED, and then this goes through a bunch of beam conditions. But the important thing is that we're launching this single beam onto the single mode polarization maintaining fiber. So it's a 15-meter non-polarization maintaining fiber. In a single mode polarization maintaining fiber, there is a slow axis and a fast axis, which are perpendicular to each other. So we condition our beam such that we can use polarizer and half-wave plate. We align our beam that is 45 degrees along this with respect to the primary axis. So by doing that, we're basically launching two spatially overlapped beams, but orthogonally polarized beam traveling inside the single mode fiber along its fast and slow axis. And so these two beams are also experience different phase modulation depths by going through a fiber EOM, which which modulate them at the same phase the frequency, but with different phase modulation depths for the different axes. And then upon the sample reflection, both beams passing through a quarter wave plate QWP, they pass through twice so that the quarter wave plate acts as a half wave plate. So the beam going forward in the slow axis will come back in the fast axis, and then forward in the fast axis will come back in the slow axis. So by doing this, both beams actually experience the same physical lengths or optical paths, because one is forward slow, coming back fast, the other one forward fast, coming back slow, but they experience different phase modulation. So this is a concept of a Sagnac interferometer where they originally was constructed about 100 years ago to detect ether. That's such that the two beams are going in a circular loop, but they're having, because of the way they have different kind of phase difference. And then we create this phase difference by a fiber EOM for phase modulator, and it's forming a Sagnac loop. and our detection is the interference signal coming back when the light comes back, and on the avalanche photo detector specified APD here. It's worth noting that our Sagnac loop is so-called a zero-loop Sagnac loop, where this is a picture from Wikipedia, but you can think about this Sagnac loop that we just basically squeezed these two mirrors together into, so there's no zero-loop area, and this will help us reducing other environments such as magnetic flux in the environment that create that could be a source of noise. Okay. So by doing such, and the key of this measurement modulation is fiber EOM phase modulation, which we can drive the modulation depths by also the modulation frequency using a fast locking. Okay. And so we tune the EOM frequency such that the EOM frequency matching the time of flight for the 30-meter non-fiber loop. So in the experiment, we tuned it around 4.5 megahertz. And then by doing such, one can calculate the interference signal, intense interference signal detecting at the avalanche photo detector. And we can look at this can be quantified by the first and the second harmonic interference signal. And then it has a very nice form mathematically. So the important thing is that for the first harmonic signal, it's proportional to the Kerr rotation. That this is a Kerr rotation that the light sees. So everything, not just the sample, but all the optics of rotation will be recorded here, and coupled to a Bessel function of 2, 5, and 5 is the modulation depth of that we can control using the locking that drives the UM itself. And also this first harmonic is also inversely proportional to the Kerr elasticity, which is the Kerr. This is basically sample reflection coefficient of the left-hand side and right circular polarized light intensity. And we're also detecting second harmonic intensity modulation, and we can work out that it also has a very similar mathematical form, in that both are inversely proportional to the Kerr elasticity, and then it's proportional for second harmonic proportional to the cosine of the Kerr rotation. Because of this simple mathematical form, we can basically measure both signals simultaneously and using one over the other, so that we can get rid of the Kerr elasticity and only detecting the Kerr rotation, everything that the light sees. Okay. So this is one of the reasons that Sagnac interferometer is so sensitive and has such a low noise, because by doing one over the other, we get rid of the intensity fluctuations that come from air current, can come from laser source intensity fluctuation, and we only detecting the Kerr rotation signal that the light sees. But I wanted to mark that this Kerr rotation, including the sample and including everything the light passes through, so our Kerr rotation always have a DC background. But that does not stop us from continuing our measurement. So I'm showing here is that now we're constructing a bilayer structure, a Spintronics structure. We're using a PMA magnet. This is a cobalt on a platinum. And we shed the laser onto the system. This is also a hall bar, but I won't spend too much time talking about the electrical measurement here. So we're first constructing, by doing this measurement on the outer plane magnets, we can measure the Kerr rotation, which is directly coupled to the outer plane magnetization, while applying in-plane magnetic field. So we start with the outer plane magnetization, and we tilt this side in-plane, so we can see this parabolic behavior. For those who are expert in metrology or Spintronics, you will see that this is very similar to the most commonly used harmonic Hall measurement, where we're basically measuring in the harmonic Hall measurement, you use a Hall readout to read out the outer plane magnetization. Here we use a Kerr rotation to read out the outer plane magnetization. So I don't have too much time to go into the details here, but I can chat afterwards. But it's important to notice that our Kerr rotation readout only coupled to the outer plane magnetization and does not couple to the in-plane moments. And we have calculated this in our paper that is because of the Sagnac interferometer, the setup interferometer, we really we don't have sensitivity of the in-plane moments. Versus for harmonic Hall measurement, you both have outer plane moments and also in-plane moment coupling through the planar Hall effect. So this is the baseline of our measurement that our Sagnac is arguably a more cleaner measurement such that we only detect the outer plane magnetization. So first here we show that the Kerr rotation is measuring the outer plane, the tilting the outer plane magnetization. And one step further, we can also measuring the tilting from the current-induced outer plane moment in motion. So here in our locking, we passing a quasi DC current, which is about a few kilohertz, onto the system, basically modulating the current in the bilayer system. And we look on the locking, we look at extra demodulation, and we only look at the Kerr rotation where we detect it at the frequency that we drive the device. So we're only looking at the tilting from the current-induced magnetic motion. And by measuring this applied external magnetic field along the x and y direction, we can couple to the either the damping lecture or the field lecture. And we can vary the external magnetic field, and the slope of the varying external magnetic field is essentially the spin torque effective field of either it's one direction along damping lecture or the other one is down the field lecture. And so by measuring the slope, we can directly quantify the damping lecture and field lecture of the outer plane magnets. Okay. So this is roughly the gist of how we quantify the spin torque efficiency of the outer plane magnets. We can also do this measurement with an in-plane magnet. Here we are again constructing the same kind of bilayer structure, but we chose the cobalt thickness such that it's this should be an in-plane ferromagnet. Sorry, this is a typo here. By doing with the in-plane magnet, the current-induced change in the outer magnetization are basically first order in the outer plane tilting angle, in the sense that this is similar to a harmonic Hall measurement. Their damping like torque corresponding to an outer plane effective magnetic field, where the field like torque gives an in-plane effective magnetic field. Because we're only sensitive to outer plane magnetization, our technique can only quantify the damping like torque. So our measurement goes. This is an example of our measurement where we were looking at the current-induced rotation delta theta k as we're applying a constant magnetic field, and which drag the magnetization in the in-plane direction. So which we're varying this cosine phi h angle, and we're doing this with different strengths of magnetic field over here at h, and we can do this. We can fit this our measurement as a nice cosine equations. And then we can using this fitting and extracting out the amplitude of the cosine function, and then plotting at 1 over mu naught h minus h M effective magnetization of the system, and h is a pi magnetic field. And using this slope, we can extract out the damping network in the system. Okay. So by doing this measurement, we essentially verify that we can conduct this measurement for both cobalt thicknesses that gives either the outer plane magnetization or the in-plane magnetization by varying the thickness of the cobalt. And we show that, roughly speaking, our quantification of the damping network are relatively consistent for the outer plane magnetization for the PMA series versus the in-plane series. And we can also measure the field network for the outer plane magnetization. And because, as I mentioned, for the in-plane moments, the field network is in-plane, so we cannot detect this using this technique. And we showed that the Sagnac readout for the damping network efficiency for those two theories are roughly consistent, which is not often the case for electrical-based measurement. This is because the fact that our Sagnac readout is only sensitive to the outer magnetization, and the electrical-based measurement also have contribution from the planar Hall, from the in-plane moments through the planar Hall resistance. And you can see details are harmonic Hall discrepancy in the first version of this paper that was posted on arXiv 2 years ago. Okay. With this, I wanted to get to almost to the end of my talk, so I just want to give a brief outlook about what our current work. We're working on conducting sound interferometer measurement in cryo and ultrafast region to really imaging those ultrafast spin torque dynamics in the van der Waals magnet materials, in the van der Waals magnets driven by those topological materials. Optics, in my view, is really an outstanding tool to provide a unique advantages over transform method, because the light directly coupled with the magnetic moment, regardless whether it's conducting or insulating. And also, we have showcased that the Sagnac rotation has this outstanding power sensitivity, and also allows you to have spatial mapping and temporal resolution we're currently developed. And it will be also a unique tool for terahertz Spintronics, because light is a natural platform for those higher frequency collinear and non-collinear AFM Spintronics. Okay. And so our group is currently working in a few directions, which is connected by these really outstanding opportunities in those multifunctional van der Waals structures for the spin-based quantum information processing. We're interested in creating next generation spin torque devices based on 2D and topological materials. And we're also working on probing the ultrafast spinning and magnon dynamics using a time-resolved RFEDs and XMCD and also RFEDs. And we're equipped with air-free integration of van der Waals materials through our collaborations and also integrating our lab in a well-controlled environment. And I'm also excited to look into different aspects of quantum sensing and control based on some of the magnetic atomic defects in these systems. Yeah. So this was my last slide. I'd like to acknowledge my postdoc advisors and PhD advisors on that some of this work are performed. And Crystal is from Oakridge Andrew May's group, and Columbia Xavier Doyle's group, and TM is performing Cornell David Miller's group. A lot of the work is done by Saba and Tal and Riley and Orion, and now our new students at USC. Yeah, so this is our team, and those are the people who did the work. With this, I'd like to conclude my talk, and thank you for your attention, and happy to take any pictures. I can take any questions.
Thank you very much for the interesting talk, and we can thank the speaker using the react button on Zooms. So this talk is open for questions. If you have any questions, please use the raise hand function on Zooms, and I will call in order. And if you're watching this on YouTube, please type your questions in the chat box, and I'll read it for you. Yeah, the raise hand function is actually also on the react button. Okay, do you have any question? Li Shu, please go ahead and ask your question.
Hi, Professor Luo. This is Li Shu Zhang. Thank you so much for your nice work. Actually, I'm quite interested about your work for the interfacial van der Waals system. You induce the FTT layer to break the symmetry of the chromium sulfide bromide. But when the charge current inject into the platinum, due to itself has a very strong spin Hall effect, the FTT layer, the magnetic moment may also flip. Have you measured the magnetic state of the FTT layer in your work?
Also, we are measuring the magnetization state of FTT through the normal Hall readout. So just like a comment that we are measuring the exchange coupling onto the FGT because our readout is mostly sensitive to the magnetization FGT. This is a Hall measurement. We think there should be exchange couple onto the constant bromide and change the canting of constant bromide as well. But for the Hall measurement, we're not sensitive to constant bromide. This is much less conducting than FGT. But we're definitely conducting other measurement right now in our lab, let's say optical measurement and other different kind of technique to try to probe the canting of the constant bromide as well. I hope that answered your question.
Okay, because I feel that if the magnetic moment of the FTT layer is also changed during the flip of the chromium sulfide bromide layer, it might have a influence. And can I ask how much the energy consumption during the field difference switching?
Oh, yeah, so we're using platinum. So our spin torque efficiency is at 0.1. So one charge 0.1% of spin. One charge 10% of spin, right? So we didn't calculate energy consumption, but we can quantify the charge to spin conversion, which is a spin Hall efficiency.
Yeah, and can I ask the switching time during this procession?
What's that?
The switching time during the flip, during the procession.
Yeah, so we don't have a measurement of that because it's a quasi DC measurement. We pass a pulse current and then we turn off the current and then we do a small DC voltage readout, a quasi DC readout, and a normal Hall measurement using of the magnetization using the Hall readout. So we don't have a direct measurement of the switching time. But I would think the switching time is close to the intrinsic magnetic dynamics of iron germanium ferrite, which is on the order of few gigahertz to tens of gigahertz.
Okay, I see. Thank you.
Great, thank you. Do you have any other question? Professor Kent, please go ahead.
Thank you for this very interesting talk. I have a question about the exchange bias.
Yeah.
Is there a direction? Is it really an exchange bias or is it an exchange field that you've shown? In other words, is it a field that's acting on the moments? I mean, when I usually think of exchange bias, I think that I'm inducing some kind of unidirectional anisotropy on the ferromagnet.
So we're measuring exchange field.
Okay,
So
so
yeah.
it's an exchange field that's canting the moments out of plane. Can you induce an exchange bias?
I'm just not aware of how to separate those two. Could you illustrate? Yeah.
Okay.
Could you illustrate how to separate these two?
Well, usually you would see this exchange bias would be that your field is it's like a a field acting on the ferromagnetic layer. So a shift of the loop left or right depending on the state of the
So this is a in-plane exchange bias or exchange field acting on outer plane magnet. So we wouldn't see a shifting in the left and right on the outer plane hysteresis.
Correct. If you don't have a bias out of plane, you wouldn't see that. Yeah.
Yeah, right. This is in plane because the chronoferromagnet is an in plane magnet, so we don't expect the outer plane bias that way.
Okay, thank you.
Yeah.
Dr. Moriarty, please go ahead.
Hi. A very nice presentation. Thank you. I've read that some van der Waals devices, graphene, when the electron density raises to Fermi level, approaching the optical phonon energy, you get a lot of scattering. Do you see any of that effect in your measurements on the first device you showed? With the energy level going into the device, can you actually detect points where the energy levels produce a lot of electron scattering?
I don't know how to measure that. Maybe to illustrate what would be the possible way to do that. Oh, I can see that our magnum modes are not sharp in the sense that there are a lot of scattering mechanisms in there. But I'm not sure how we can directly measure the electron scattering.
Yeah, I would think maybe the resistance goes way up, maybe more sharply than, or maybe you see a big change in the resistance.
We do see a change in resistance as due to the magneto-resistance, the commonly magneto-resistant readout. That's a spin-dependent filtering, spin-dependent magnetic scattering. So we do see that. That's the base of our measurement. Yeah, that's that. But we see that for all the sort of resonance mode that we're detecting. Yeah.
Okay.
Yeah. Yes.
Thank you.
Great. Do you have any other question? I just have one quick question. I think on slide 19,
Sure.
where you showed the ferromagnetic resonance spectrum, and
So take a look. Okay.
yeah, this one. Yeah, so the left side and right side is neither symmetric or anti-symmetric. Did I miss anything? So is it supposed to be like that?
They're supposed to be like that. So we're extracting out the anti-symmetric and the symmetric part that give us the different damping network. But actually, I think more about this question.
Okay.
Yeah.
I think I got some question in the chat. On slide 32, can you tell us how exactly the TC was determined?
Sure, 32.
Yes.
Oh, the TC was determined, so you can see the TC of the FGT by where we lose the outer plane hysteresis, essentially. So when we lose the outer plane hysteresis, that's when the FGT argumentera become non-magnetic. Yeah.
Thank you. I hope this answers the question.
I have a question.
Yeah.
Yeah, go ahead.
Please.
Hi, Kelly. Thanks very much for a nice presentation. Can you go to slide 12?
Sure.
Yeah, so you said that there are two modes. There is like, I think this one maybe slide 12 before. Yeah, about this acoustic mode, because I'm a little confused. I mean, when you say acoustic, you refer to phonons, or, I mean,
Oh, no, these are just acoustic in the sense that they're in phase.
because I
Yeah.
was say acoustic, I mean, usually when you say phonon, it's high frequencies. I mean, that's why I was confused.
Oh, yeah. But these are fundamental magnet modes. They're not. These are
And the optical mode, and then it's just like just magnon mode, but with different.
right,
So,
different phase. Yeah, one is in
Okay.
phase, one is out of phase. Like acoustic in phase, out of phase, optical is out of phase. This has no direct relation with phonons.
okay, sounds good. I mean, thanks for clarification.
Great. Do you have any other question? Okay, if we don't have any immediate question, I want to say we have another session shortly after this for further discussion. It's gonna be off the record. But if there's no other burning questions, I would like to thank the speaker one more time. And I want to thank you all for participating. We're going to stop the recording now. And if you have any other comments or discussions, feel free just to turn on your mic and continue the discussion.